I know deep down that I can do this work because of taxpayers and because of the support of, the Emory and Georgia Tech and also the federal government. I guess what I would want the public to know is that I'm grateful for the resources that they share with the university, and I really am working hard to make sure that they get something out of it.
Welcome to Holy Shift, Biomedical Breakthrough Shaping Tomorrow. What is biomedical engineering exactly? It's about engineering solutions that improve human health, from new medical imaging tools to personalized cancer treatments. Holy Shift reveals the people, passion, and purpose powering the future of biomedical research. Today's guest is Dr. David Myers, a biomedical engineer who builds tiny technologies to solve big medical problems. He works across Georgia Tech, Emory, and Children's Healthcare of Atlanta, where his goal is simple but powerful: create new sensors that doctors can use to help patients. We're talking about his journey into research, what it's like working where engineering meets medicine, and how microscopic devices could change the future of healthcare. So, welcome to Holy Shift, Biomedical Breakthroughs Shaping Tomorrow. We have Dr. David Myers here with us. Why don't you tell us about yourself and why you're here today?
Sure. I'm David. I'm an assistant professor of biomedical engineering at Emory and Georgia Tech. And I'm here to talk about small things.
Small things.
Because I like small little things. That's what gets me excited.
Okay, that's really cool. I have to also plug the fact that you have a very thriving Instagram and TikTok channel.
I do.
What is the name of it? Because we're just going to dig really quick into this because you just had me laughing in stitches. What is the name of it, and what inspired your lab to begin posting these?
Yeah, it was the Pioneers. And so we're on TikTok and we're on Instagram. And where I started was I just felt that academic life is actually just like everybody else's life. It's just got these little weird nuances. And I wanted the public to know that scientists are people and they're goofy and they come in all shapes and forms and sizes. And we just wanted to share some of our antics with the world.
Okay, yeah. So we will include links to it in our show notes. And listeners, I definitely think you could scroll through some of them. If you definitely want to laugh and maybe understand some quirky parts about science and scientists, check it out. So now thinking about that quirky stuff and interesting stuff about Dr. David Myers, tell us about the small things that you work on.
I work on microsystems. And so microsystems are It's a very broad field, but very interesting things happen at the microscale that we can take advantage of.
What's an example for someone in thinking about microsystems? What's the size of a microsystem how would you describe that to something someone would say, yes, I understand?
It's usually less than a millimeter.
Okay.
And what happens is
How big is it, like a grain of rice?
Ooh. Oh, man, I'm stumped already.
Love it.
Jeez. Angela, I'm trying to stay a professor. I'm going to get fired. Okay, I think a grain of rice is probably a couple millimeters.
Okay.
So
smaller than that. Yeah.
So we're getting to that size scale. But, for example, if you take a microsystem and it's got liquid inside of it and you shake it, that liquid doesn't move around. Whereas if I take my can of Coke and I shake it, it's going to go all over the ground here. So there's these really interesting tiny phenomenon that happen that we can take advantage of. Usually to make I'm really interested in stuff that goes to the clinic and leaves the lab and doesn't stay on my bench.
Okay, so tell us a little bit, because I know also you're doing some commercialization efforts and stuff in your lab. So why don't we do this? We're going to peel the onion a little bit.
Okay.
And let's start with when you were 5 years old, is this what you wanted? What did you want to do when you were 5 years old?
Oh, man. Let's see. I come from a family of engineers and my mom is a nurse. And so engineering was something I was interested in as pretty much my entire life. I decided on mechanical, much to the chagrin of my father, because I had an uncle and he worked at a bearing plant. And he took me into this bearing plant, and he literally reached under his desk and he put this box of widgets on his desk. And it had everything in it. It had otoscopes, it had parking meters, it had bearings from steering columns, and these were just projects that he worked on. And I learned really around my teenage years that I liked seeing things move, and I liked learning how things move. And mechanical engineers get to basically study this as a career option. My uncle literally figures out why stuff works and doesn't work, and so he kind of inspired me down that path.
What kind of engineer was your dad?
Civil and computer.
Oh, okay. I get computer. It now. There is a little bit of...
Yeah.
I mean, but, I'm a biomedical engineer, so I personally think biomedical engineering is the best of the best. I'm biased. So, and the thing I love about biomedical engineering is we get to collaborate with people from so many different backgrounds and bring all those pieces together.
Yeah.
So tell us how you got from...
Mechie to...
There we go.
There we go. Okay, so... This is a long story. Buckle up.
Okay, I'm ready.
It's got everything in it. It's got pain and sorrow and happiness and joy. So I was a young undergraduate. I was sitting in an electrical engineering class at Virginia Commonwealth University. And I remember this moment. I had thought about grad school. I'd thought about, I really thought I wanted to teach. I love teaching and being around people. Mm-hmm. And this professor shows a picture of a spider mite. And a spider mite is less than a millimeter.
But smaller than a grain of rice.
Smaller than a grain of rice. Right. I think we've established that, right? But what's really exciting is right next to that spider mite was a gear train. And I was like, how did they make a gear train smaller than a spider mite? Wow. And that it was so exciting and interesting that I was like, that's what I want to do. And I applied to grad school. And long story short, I ended up in grad school at Berkeley. And Berkeley does a lot of this type of microsystems research. And I spent my whole PhD studying microsystems.
Okay.
And in particular, I studied strain gauges, which a strain gauge is a widget that when you put it on something, it tells you how much force or how much strain is in that member.
So what are some common uses of strain gauges?
So that's really the problem. That's the problem. So what happened was I was so excited and I was doing all of this research and I got to the very end of my PhD and I ended up talking to different people along the way. I talked to business people, and they were like, David, nobody's going to use the strain gauge that you're making. It's like, but you're a helicopter manufacturer. Don't you want to put this strain gauge on your complex helicopter parts to know how much force is on them? They're like, no, it's too much work. It's like, oh. But, I was undeterred, and I kept going, and I kept going. And I had this one fateful meeting with a professor from Carnegie Mellon. Mm-hmm. He had come to visit Berkeley, and he very graciously had made a few minutes at the end of his day to just meet with the grad students from anywhere. So I set up this appointment, and I was really interested in a faculty position, and I'd been studying these microsystems. And I go in, and I'm like, hey, professor, and I will leave his name off. He knows who he is, because I told him this story later. And I sat down with him, and I said, I'm interested in faculty positions, and I saw your university has faculty positions open right now. And this is a common ploy that young, inexperienced grad students will use to see if they might be a good fit for this institution. Mm-hmm. So the professor, without missing a beat, he goes, David, what are you working on? And I pour my heart out to him. I'm like, I built this little thing, and I built this lid for this little thing, and I built this force sensor, and I'm going, like at least 2 minutes. And he just looks at me, and at the very end of it, he goes, who cares? And you just feel the life just drain out of you. Right, that's like those gut punch moments. You're like, what happened? And it was really in that moment that one of the things that's tough for scientists is, we have to, one of the fun things, but one of the difficult things is we often don't know if what we're working on will be useful to society.
Yeah.
And so one of the things that we do is you get really good at technical and building little things or building this or that, but you also have to answer this broader question, does the thing that I have made excite people? do they want to see it? Do they? And so that kind of started this new part of my journey where I realized I needed to figure out whether what I was putting my efforts into might be something that someone else wants or needs or wants to do. So at kind of that moment, after a long introspection, I came to the conclusion that I would really like to do more biomedical work. And I'd seen at Berkeley, there were these phenomenal scientists that took microsystems and then applied them to biomedical research. And I was like, well, maybe that's what I should do. And so what happened was, I'm at Berkeley, and I started just bugging everybody that would listen to me and asking for some sort of connection to the biomedical field. Because I was in a very traditional mechanical engineering. And as you know,
yes,
there's a really big difference. Even though a mechanical engineer is abbreviated ME and a biomedical engineer is BME, there's a really big difference with that B. I will say that I was met with a lot of rejection, and I couldn't find a place, and I was getting really dejected. And finally, this committee member, I swear he had been avoiding me because I had been bugging him so much. And this committee member, he sees me sitting kind of dejected at a talk, and it's a biomedical talk, and I think it's really interesting, but, I'm starting to feel kind of desperate. And the committee member goes, "Oh, David!" I'm like, "Yes!" He's like, "What are you doing after this talk?" I'm like, "I'm free," because I didn't have anything else going on at the moment. He's like, "Come to my office right after this talk." And I'm like, "Okay, no problem. I will go with you after this talk." So what happens is...
I'll check my schedule.
Yeah. It's empty. Weird. So talk ends. I have no idea what the rest of the talk was about because my brain is spinning. I'm like, what is it? And I go to his office. He goes, "David, I met this guy. He's amazing. What are you doing? Are you free right now? Come on, let's go." And the professor launches out of his seat, marches out the front of the building, and I'm just in tow, don't know what he's doing, but I'm just following him. And he starts talking along the way. He's like, "There's this guy. His name is Wilbur. Wilbur just got a faculty position at Biomedical Engineering. And you've got to meet Wilbur because he's looking for someone that likes to build small things for biomedical research." And I'm like, okay. And so we're just going along. And what I love about older faculty members is they walk around like they own the place. So he's just walking across Berkeley's campus. He goes up to the bioengineering building, just walks right in, and he walks up to this huge set of double doors. They were at least 12 feet by 6 feet across each, two of them. And he just slams on it. Boom, boom, boom. And then he just looks at me like this. And we're just standing there, and the door opens.
That was Wilbur at Berkeley.
And so what happens is, he just keeps going. The door opens. He's like, "Thanks." And he just walks right in. Wilbur's sitting there at a bench working, and he just goes right up. He goes, "Wilbur, this is David. David is one of Al Pisano's students. David makes small things. You need a guy that makes microsystems. Hey, Wilbur, this is David. David really wants to do biomedical research." And then I kid you not, the man crosses his arms, and he looks at the both of us, and he starts shaking his head.
I can picture this. I can totally picture
So there's
this.
Wilbur and me stunned, looking at each other like, what the heck is going on? And Wilbur finally, after a pause, is like, "You want to meet for coffee?" And I'm like, "Yeah, let's meet for coffee." And so we met at a coffee shop in Berkeley, and he actually came to my PhD defense.
Nice.
And he was like, "Hey, I'd like you to come work in my lab." So I followed Wilbur in tow. My wife is ridiculously pregnant at this point with our first child. So we left California on the last day that she was allowed to travel.
Oh, wow.
She still remembers this when we stopped I had to stop in the Grand Canyon on the way. So, of course, yes. So she's glad for it. Probably could have done without the pregnant part. So anyway, we made it, and we got here, and that started kind of the very beginning of my biomedical journey.
Yeah, that's nice. And I'm pretty confident we will have Dr. Lamb on this podcast soon.
I hope so.
So we'll have to tag both of these two episodes together.
Yeah. You can ask him if he was as shocked as I was.
We cannot give him the heads up, though. Deal?
Okay, yeah.
Okay. No, mom's the word. Okay.
Yeah.
So when you think about going from something that could potentially be used on a helicopter to now utilizing something where you're doing researching on like testing and stuff like that in the lab. What does that look like on your day-to-day schedule?
One of the biggest things is that when you're designing something to work in helicopter and more physics and aerospace applications, usually you just need to make it work once, and then someone else will take care of making that thing work for you again.
Yes. Okay.
When you have to be the person using your own widget,
Yes. Yeah.
it gets a lot harder.
Yeah.
And you have to build a widget that you can come into the lab every day and reliably use so that you can, and that takes a lot of time. And it's something that I think that was one of my biggest realizations in going from research more on the physics side to the biomedical side, is that when I build a widget that we have to use, sometimes it takes me a year or two to figure out how to get it to reliably work so that I can get good testing with patient samples.
Yeah, exactly. And I think to me, that's one of the special things about adding that B, right? That biomedical piece of it. Because the human body, we've had several episodes where we've talked about personalized medicine.
Yeah.
And how, for example, your brain works different than my brain, or your cells may react to something differently than what mine will. And the value of understanding that. But there's also that challenge to the piece, because you have to accommodate for that.
That's right.
And have something that's standard enough that works.
Right.
So tell us, what is it then? Like, why should people care about the research you're doing? The what? Because that's what I tell my master's students when they present something. I'm like, so what?
Yeah. Okay. So I have a lot of projects. So I'll just pick a few that we work on the so what a lot. So a good example is when I was a young assistant professor, I was sitting in my office, and all of a sudden I heard a knock at my door, and this gentleman comes barging in and goes, "Hey, David, my name's Jesse Wagner. I work down the hall from you. Listen, I was talking to Wilbur. He told me about you. I think we get along really great. We should start working together. What do you think?" Okay. And Jesse and I did start working together, and we've had a lot of fun. And so one of the neat projects that we've worked on together is Jesse is really interested in this, in infectious diseases. And one of the things that I find fascinating is we know that all life has these nucleic acids, DNA and RNA. What I did not know is two big things. One, just about every life form has a very specific sequence of nucleic acid that only that life form has. So, for example, viruses, you can identify a virus by a very specific little sequence, and only those viruses have that sequence. So that's the first thing I didn't know. And the second thing I didn't know is that it's actually really easy to test for that. But the thing that's hard is getting the nucleic acid around. And so what happens is, especially for there's one form of nucleic acid, it's RNA. It's very difficult to transport without keeping it really, really cold. So Jesse had been working on an approach that would allow us to transport DNA and RNA at room temperature. And that could be
which pause is huge, and we've done work together. So hence,
yes, so
we've had this conversation. I know how huge, but it's huge because when you need that, otherwise, if you have to have it at some freezing temperature, and then you need to put it on a plane, and then you need to get it somewhere else, and this is valuable information. And if anything happens in that chain of command that drops the temperature, it's wasted.
It's wasted,
and it costs thousands upon thousands of dollars.
Right.
Slowly impacts the potential cures and stuff that we can have. So being able to do something at room temperature is huge.
That's right, because now you can drop a sample in an envelope versus having to have really, like you were saying, it's like an extensive cold shipping. And so what's exciting is now you could imagine that different parts of Georgia, it's not just the Atlanta and Columbus area that have all the access to great tests.
Right.
Everybody can have great access to tests, and they can learn, hey, I've got these weird symptoms. Well, we can test for that now. at a really cost-effective manner.
Right. You can be at home at some point. You can be at home, submit a test, and mail it in versus have to sit on 75, 85 for an hour and a half to get to Emory, to park, to wait in the waiting room, to go to the lab, to then turn around and do it all over again.
That's our goal.
And that does sound like a high-end problem, but so much of the U.S. One of the things that I think when some individuals hear about this, they think we're only focused on maybe low to middle income countries. Okay, which there's a lot of value. We have a lot of value in that.
Yeah,
however, we forget that so much of the U.S. is rural.
That's
that
right.
They are not close to things. And all of our fellow citizens in the U.S., the impact this could have on helping them live a better life, a healthier life, a prolonged life,
That's right.
and improve their community is huge.
Yeah. That's actually something we're really excited about.
Yeah, I am too. Yeah. I'm really excited.
It's a long-term goal, and I think one of the, there's a lot of things that I don't do because it's not convenient. And so if we can just make access to health convenient, how much better life could everybody be living?
Yeah.
So that's one of our goals.
So let's talk a little bit about then funding for this, because we're now in 2026.
Mm-hmm.
Funding for anything has had its waves of focus areas, and last year was a very difficult time for funding. We're entering into 2026. So can you tell us a little bit more about how you get funding for the work you do, and maybe what would happen if you weren't able to get funding?
Oh, yeah, that's a great question. So we typically write to the National Institutes of Health. We found that one of the things that I love about Emory and Georgia Tech, and also just to speak more broadly for being in a university, I know sometimes the university can be really mystifying because you're like, why do you need to go to a university to do research? But one of the things it gives you access to is these kind of serendipity encounters, which you can see my entire life has almost been defined by these serendipity encounters. And so I never imagined me as an engineer interested in small gears working with an infectious disease doctor to improve access to healthcare in rural parts of Georgia. But along that line, the university typically, we all work together to apply to the National Institutes of Health. And I think one of the things that I've noticed is, the first time I had to start thinking about how much salaries cost, and we always think of funding as this amorphous, like, oh, that's $1 million. And when you start thinking about a salary over 5 years, you realize it doesn't go that far. Yeah. So really what funding pays for today is for people. And it pays for, it typically pays for young trainees to do some really cool research and learn how to become independent researchers themselves. So it's designed to be a win-win. And without that funding, if that were to go away, it would it just slows everything down. Yeah. It would be a lot more difficult to make a lot of these breakthroughs because there's just less time and effort and energy available for each problem.
Yeah. And when we slow things down, then it means that a cure that we could have in 5 years, instead we're going to have in 15 years.
Yeah.
That it is not a 1-to-1 ratio in that piece, right?
Yeah.
And I think that is something that is important to understand. Tell us a little bit about some of the people that work in your lab.
Yeah.
And where do some of them go when they graduate and move on to different things?
Yeah. So let's see. So I have a couple of different graduate students. They've come from all walks of life. And I've had a few postdocs. Postdocs are individuals that have had graduate training and they have a PhD and now they want to do just a little bit more time researching before doing something else. And I had one go to Kimberly-Clark, and I had one that went to Intellia for a while. Intellia is this really interesting DNA editing company. Let's see. Yeah, my trainees go...
Well, they definitely make amazing videos for Instagram and TikTok.
That's true. They do. Yeah. We spend a lot of time a little bit of time on that.
Well, I think think we should all have fun and enjoy the things that we're doing. So in thinking about that, having fun and why that's very important, because there are times when what you really hope would work do not work. And that is very disheartening and depressing.
Yes, it is. You've
experienced that once, right?
Oh, yeah, many times. Yeah.
So how do you get through that? And I think also, how do you as a leader, how do you help others learn how to stay inspired despite the fact that so many experiments don't turn out the way that we think they will?
Yeah. I have experienced experiments not working. I've experienced experiments not working because I was sure that it should work a certain way, and I kept not getting the answer that I went in biased that I expected. One of the things that happens is after you've done it once or twice, and especially when you've been through a long slog, and I will be honest, my first slog when I started with really traditional mechanical engineering until I finally had a widget. So when I worked with Wilbur Lamb, we made a strength test for platelets.
Okay.
And platelets are these enucleate cells responsible for clotting.
I could see how your strain would work.
There, that's right. That's right.
Okay.
It was like a force sensor,
Yes.
a platelet force sensor.
Yes.
But it took me a couple of years of just slogging, and it was like, nope, that was wrong. Nope, that was wrong. Nope, that was wrong. Yeah. And once you get through it once, it usually makes it a lot easier.
Yeah.
My main strategy as a leader is very quickly, these moments of failure, the stakes get really high. Because when you're in that moment of failure, you're like, my life is over. I'm never going to amount. I mean, it can get dark quickly. Absolutely. And I think one of the strategies that I work on in the lab is just constantly trying to give perspective and bring the stakes down. Like, it's okay to fail. It's okay to learn. It's not a complete wash. Research goes like this. And sometimes just knowing someone that has been through this before, that it's going to happen this way, it can be very comforting.
I've said this before on this podcast, I believe, but it reminds me of, I think it's the Thomas Edison quote when his lab burned down. And he was like, that's great. Just burn down all of our mistakes. Right. And I love those things because we only remember as a society the successes of certain areas. We don't realize all that goes into it ahead of time. So speaking of successes, what are some successes that you're proud of that your lab and your work has done?
Let's see. So many. No, sorry. I was really excited when, working with Wilbur Lamb, when we made our first strength test for platelets, one of the things that was really exciting for us was when we started testing patient samples, there were these certain patients that have a bleeding disorder. We know they have this bleeding disorder. Mm-hmm. We've never really understood why and what causes this bleeding disorder. Mm-hmm. And working with Wilbur, it was the first time that we showed a link between, we measured these platelets, and they just had wimpy platelets when they were bleeding. Ah. And that was it. And it was really fascinating that physics was very closely linked to something very physiologic, like
so your
bleeding.
Helicopter strain actually helped.
It actually worked out.
It totally did.
Yeah.
So if someone has this, then what can you do to then, if you identify it, how can you make a positive impact on that individual's life?
Well, it's neat. What I love about this story is it's ongoing. But one of the things that happens is when you finally can measure a difference between someone, you can say, hey, you're bleeding, you're not bleeding. And I have something that I can measure. Mm-hmm. Now I can start learning what may be causing the bleeding or what may be causing the not bleeding. And what was really fascinating was a follow-up work that Wilbur's and my MD PhD student did. He found that in this disorder, there are these proteins that circulate, antibodies, and they're typically responsible for the immune response. Mm-hmm. But these antibodies were actually binding onto platelets. But what was really fascinating was these antibodies, the way they interacted with the platelets, they could actually make the platelets stronger and actually help confer resistance to bleeding. Okay. And they also can make the platelets weaker and actually enhance bleeding. So while we don't know exactly what to do with this, what's fun is that this basic research project where you just started linking the strength of a platelet, and then you started asking, why is the strength changed? Now we actually starting to learn more about the disorder and how the antibodies might be playing a role in it.
Yeah, and this can be translated into other disorders that it could have significant implications in that effect. Okay, so what do you do when you're not inside the lab working on these projects? What do you do outside the lab?
Ooh, mostly family time. I'm the family chef.
What's your favorite meal?
Oh man,
That is hard. I can only imagine.
yeah, I've got a really wicked deep dish pizza. I'm pretty proud. It's a pan pizza, so it's easy and it's delicious. That's fun. So let's see, we make a lot of pizza, and outside of the lab, it's just I've got a 14-year-old, so he's in high school, and we do high school things. So he was really into wrestling this past season, so we did wrestling. And I've got an 11-year-old, and she's really into she's really into jujitsu.
Oh.
And it's wonderful.
I love this.
And actually,
Yes.
one of the funnest things I will hear is that we will be sitting, we can hear the coach, and the coach will actually yell, "Ellie," my daughter's name, "why are you so mean?" And I just, I'm okay with that.
Girl.
I'm okay with that. Yeah.
Yes,
So.
I love it. Okay, so tell us, David, what do you want to make sure the listeners, when they tune out of this episode, if they only remember one thing about the work that you do, why it's important, and why it should be supported, what would you want that to be?
I would want them to know that I'm very grateful for the opportunity to do this type of work. It does involve a lot of sacrifice. It's a lot of long hours. But I know deep down that I can do this work because of taxpayers and because of the support of the Emory and Georgia Tech and also the federal government. And that one of the things that's interesting is, sometimes academic research can feel really glacial. But for me, as a child born in the 80s, my life is dramatically different. I started out with a record player and then moved on to tapes and CDs and MP3 players, and I got to experience all of those along the way. And a lot of that's academic research that goes out into the world. So I guess what I would want the public to know is that I'm grateful for the resources that they share with the university, and I really am working hard to make sure that they get something out of it.
I love that. It's an opportunity to build a legacy, making a positive impact on humanity is such a special opportunity.
Yeah.
And to be able to participate in it is huge.
Yeah.
Is huge. Well, that is amazing. So what we will include in the show notes, listeners, are the links to, of course, the TikTok and Instagram. We will also include the links to your lab. Do you have a lab website?
I do.
Yep. And I know you're
More shenanigans. Yep.
Yes.
Yep.
And also the research that they are doing. I know you also have a company website.
That's right. Yes.
I happen to know because the program I run helped fund.
And I'm so grateful for that.
So we will include those in the show notes. Listeners, if you have any questions or comments, please make sure that you put those in as well. We would love to connect you, especially if you're interested in trying to make an impact on the science that Dr. Myers is doing. And until next episode, thanks for joining us for this episode of Holy Shift, Biomedical Breakthroughs Shaping Tomorrow. That's it for this episode of Holy Shift, Biomedical Breakthroughs Shaping Tomorrow. If today's conversation sparked your curiosity, pass it along to someone eager to explore the power of research to change lives. As a reminder, the opinions expressed in this podcast are those of the host and guest and do not represent those of any organization mentioned. Be sure to follow or subscribe wherever you get your podcasts so you never miss an episode. To learn more about the research featured on this show, visit bme.gatech.edu or check the show notes for links and resources. Thanks for listening, and remember, behind every innovation is a purpose, a person, and a powerful story.